So this lecture is going to be on reinforcement learning. I will, in the interest of time, skip the quiz. So the way to think about how reinforcement learning fits into what we've done so far is, remember this class has this picture, right? So we talk about different models, and we talk about different algorithms, inference algorithms, to be able to predict using these models and answer queries. And then we have learning, which is how do you actually learn these models, right? So every type of model we go through, we have to kind of check the boxes for each of these pieces. So last lecture, we talked about Markov decision processes. This is a kind of a modeling framework. It allows you to define models, for example, for crossing volcanoes or playing dice games or taking trams. What about inference? So what do we have here last time? We had value iteration, and which allows you to compute the optimal policy, and policy evaluation, which allows you to estimate the value of a particular policy. So these are algorithms that operate on an MDP, right? And we looked at these algorithms last time. So this lecture is going to be about learning. I'll just put RL for now. RL is not an algorithm. It's a kind of refers to the family of algorithms that fits in this week. But that's the way you should think about it. RL allows you to either explicitly or implicitly estimate MDPs, and then once you have that, you can do all these inference algorithms to figure out what the optimal policy is. Okay, so just to review, so what is an MDP? The clearest way, remember, to think about it is it's in terms of a graph. So you have a set of states. So in this dice game, we have in and end. So we have a set of states. From every state, you have a set of actions coming out. So in this case, stay and quit. The actions take you to chance nodes where you don't get to control what happens, but nature does, and there's randomness. So out of these chance nodes are transitions. Each transition takes you into a state. It has some probability associated with it, so 2/3 in this case. It also has some reward associated with it, which you pick up along the way. So naturally, this has to be 1/3, 4. And remember last time, this was probability 1, 10. Okay? So, and then there is the discount factor, which gamma, which is a number between 0 and 1, tells you how much you value the future. For default, you can think about it as 1 for simplicity. Okay, so this is a Markov decision process. And what do you do with one of these things? We have a notion of a policy, and a policy, let's see, I'll write it over here. So a policy denoted pi, let me use green. So a policy pi is a mapping from states to action. It tells you, a policy, when you apply it, says, when I land here, where should I go? Should I do stay or quit? If I land, well, I mean, this is kind of a simple MDP. Otherwise, usually it would be more states. And for every state, blue circle, it will tell you where to go. And when you run a policy, what happens? You get a path, which I'm going to call an episode. So what do? You start in state S0. That would be in this particular example. You take an action, A1, let's say stay. You get some reward. In this case, it would be 4. You end up in a new state, S1. And suppose you go back to in, and then you take another action. Maybe it's stay. Reward is 4 again, and so on, right? So this sequence is a path, or in RL speak, it's an episode. Let's see. So let me erase this comment. And so this is an episode. And until you hit the end state. And what happens out of an episode, you can look at a utility. We're going to denote U, which is the discounted sum of the rewards along the way. right? So if you stayed 3 times and then went there, you would have a utility of 4 plus 4 plus 4 plus 4. So that would be 16. Okay? So but last lecture, we didn't really work with the episodes in the utility because we were able to define a set of recurrences that computed the expected utility. So remember that we want to, we don't know what's going to happen. So there's a distribution, and in order to optimize something, we have to turn it into a number. That's what expectation does. So there's 2 concepts that we had from last time. One is the value function of a particular policy. So v pi of s is the expected utility if you follow pi from s. What does that mean? That means if you take a particular s, let's take n, and I put you there, and you run the policy, so stay, and you traverse this graph, you will have different utilities coming out, and the average of those is going to be v pi of s. Similarly, there's a q value, expected utility if you first take an action from state s and then follow pi. So what does that mean? That means if I put you on one of these red chance nodes and you basically play out the game and average the resulting utilities that you get, what number do you get? Okay? And we saw recurrences that related these two. So v pi of s is recurrence, the name of the game is to kind of delegate to some kind of simpler problem. So you first look up what you're supposed to do in S, that's pi s, and that takes you to a chance node, which is s comma pi sub s. And then you say, hey, how much utility am I going to get from that node? And similarly, from the chance nodes, you have to look at all the possible successors, the probability of going into that successor, of the immediate reward that you get along the edge, plus the discounted reward of the kind of the future when you end up in S prime. Okay. So any questions about this? This is kind of review of Markov decision processes from last time. Okay. So now we're about to do something different. Okay, so if you say goodbye to the transition and rewards, that's called reinforcement learning. So remember Markov decision processes, I give you everything here, and you just have to find the optimal policy. And now I'm going to make life difficult by not even telling you what rewards and what transitions you have to get. Okay, so just to give a kind of flavor of what that's like, let's play a game. So I'm going to need a volunteer. I'll give you the game, but this volunteer, you have to have a lot of grit and persistence because this is not going to be an easy game. You have to be one of those people that even though you're losing a lot, you're still going to not give up. Okay, so here's how the game works. So for each round, R equals 1, 2, 3, 4, 5, 6, and so on. You're just going to choose A or B. Red pill or blue pill, I guess. And you move to a new state. So the state is here. And you get some rewards, which I'm going to show here. Okay? And the state is 5, 0. That's the initial state. Okay? So everything clear about the rules of the game? That's reinforcement learning, right? We don't know anything about how. Okay, so any volunteers? How about you in the front? Okay.
A.
A. Okay, let me click start. A.
A. A. B. 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 A.
It's an MDP, so in that case that helps.
B. 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 Just infinitely click B. And then A, I guess. I feel like I'm losing a point every time.
I warned you. Okay.
A. 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 B. No. A. 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 A.
Yay, okay. I'm glad this worked because last time it took a lot longer. But so what did you have to do? I mean, you don't know what to try, so you try A and B, and then hopefully you're building an MDP in your head, right? Yeah, right. Okay, just smile and nod. And you have to figure out how the game works, right? So maybe you notice that hey, A is decrementing and B is going up, but then there's this other bit that gets flipped. So kind of you figure this out. And in the process, you're also trying to maximize reward, which apparently I guess it doesn't come until the very end because it's a cruel game. Okay, so how do we get an algorithm to kind of do this, and how do we think about doing this? So just to kind of make the contrast between MDPs and reinforcement learning sharper. So Markov decision process is an offline thing, right? So you already have a mental model of how the world works. That's the MDP. That's all the rewards and the transitions and the states and the actions. And you have to find a policy to collect maximum rewards. You have it all in your head, so you just kind of think really hard about what is the best thing. It's like, oh, if I do this action, then I'll go here and look at the probabilities, take the max or whatever. So reinforcement learning is very different. You don't know how the world works, so you can't just sit there and think because thinking isn't going to help you figure out how the world works. So you have to just go out and perform actions in the world, right? And in doing so, hopefully you'll learn something, but also you'll get some rewards. Okay, so to maybe formalize the paradigm of RL, so you can think about it as an agent. That's you. And you have the environment, which is everything else. That's not the agent. The agent takes actions. So it sends action to the environment, and the environment just sends you back rewards and a new state. And you keep on doing this. So what you have to do is figure out, first of all, how am I going to act? If I'm in a particular state, st-1, what action should I choose? Okay, so that's one question. And then you're going to get this reward and observe a new state. What should I do to update my mental model of the world? Okay, so these are the main two questions. I'm going to talk first about how to update the parameters, and then later in the lecture, I'm going to come back to how do you actually go and explore. Okay, so I'm not going to say much here, but in the context of Volcano Crossing, just to kind of think through things, every time you play the game, right, you're going to get some utility. So so this is the episode over here. So ARS, you're going to sometimes fall into a pit, sometimes you go to a hut, and based on these experiences, if I hadn't told you what any of the actions do and what's the slip probability or anything, how would you kind of go about kind of solving this problem? That's the question. Okay, so there's a bunch of algorithms. I think there's going to be 1, 2, 3, 4, at least 4 algorithms that we're going to talk about with different characteristics. But they're all going to kind of build onto each other in some way. So the first class of algorithms is Monte Carlo methods, right? Okay, so whenever you're doing RL or any sort of learning, the first thing you get is you just have data. Let's suppose that you run even a random policy. You're just going to, because in the beginning you don't know any better, so you're just going to try random actions. And but in the process, you're going to see, hey, I tried this action and it led to this reward and so on. So in the concrete example, just to make things a little more crisp, it's going to look something like in, and then you take, you did, let's see, let me try to color coordinate this a little bit. So you're in, you do stay, and you get a reward of 4, and then you're back in, you do a stay, and then you get 4, and then maybe you're done, you're out. Okay, so this is an example episode, just to make things concrete. So this is S0, A1, R1, S2, S1, keep on incrementing too quickly, A2, R2, S2, okay? Okay, so what should you do here? All right, so any ideas? Model-based Monte Carlo. So if you have the MDP, you would be done. But we don't have the MDP, we have data. So what can we do? Yeah.
From that data?
Yeah, let's try to build an MDP from that data. Okay, so as key idea is estimate the MDP. So intuitively, we just need to figure out what the transitions and rewards are, and then we're done, right? So how do you do the transitions? So the transition says, if I'm in state S and I take action A, what will happen? I don't know what will happen, but let's see in the data what happened. So I can look at the number of times I went into a particular S prime, and then divide it over the number of times I attempted this action from that state at all, and just take the ratio. Okay, and for the rewards, this is actually fairly easy because when I observe a reward from S, A, and S prime, I just write it down and say that's the reward. Okay. Okay, so on the concrete example, what does this look like? So remember, now here's the MTP graph. I don't know what the transition distribution or the rewards are. So let's suppose I get this trajectory. What should I do? So I get stay, 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 and then I'm out. Okay? So first, I can write down the rewards of 4 here. And then I can estimate the probability of transitioning. So 3 out of 4 times I went back to n. 1 out of 4 times I went to n. So I'm going to estimate this as 3/4, 1/4. Okay, but then suppose I get a new data point. So I have stay, stay, end. So what do? I can add to these counts. So everything is kind of cumulative. So 1 more time I went into n, and another time I went to n. So this becomes 4 out of 6, 2 out of 6. And suppose I see another time when I just go into n. So I'm just going to increment this counter, and now it's 3 out of 7 and 4 out of 7. Okay, so pretty simple. Okay, so for reasons I'm not going to get into, this process actually converges to the. If you do this kind of a million times, you'll get pretty accurate. Yeah, question?
Are we saying here that we don't know the transition probabilities and the reward, but do we know the number of states and the actions we can take?
Yeah, so the question is, you don't know the rewards or the transitions, but yes, you do know the set of states and the actions. Set of states, I guess you don't have to know them all in advance, but you will just observe them as they come. The actions you need to know because you're an agent and you need to play the game. Yeah, good question. Okay, so yeah.
Does this also work with variable costs? Like there's a probability, or variable rewards rather? There's a certain probability you get some reward, and a certain probability you get a different reward?
Yeah, so the question is, does this work with variable rewards? And if the reward is not a function of the SA, S prime, you would just take the average of the rewards that you see. Yeah. Okay, so what do you do with this? So after you estimate the MDP, so all you need is the transitions and rewards. Then now we have MDP. It may not be the exact right MDP because this is estimated from data, so it's not going to match it exactly. But nonetheless, we already have these tools from last time. You can do value iteration to compute the optimal policy on it, and then you just, you're done. You run it. In practice, you will probably kind of interleave the learning and the optimization, but for simplicity, we can think about it as a 2-stage where you gather a bunch of data, you estimate the MDP, and then you are off. Okay, there's one problem here. Does anyone know what the problem might be? You can actually see it by looking on the slide. Yeah.
Well, with your base policy of always staying, you'll never explore the quit branch of the world.
Yeah, you didn't explore this at all, so you actually don't know how much reward is here. Maybe it's like 100, right? So this is this problem, this kind of actually pretty big problem, that unless you have a policy that actually goes and covers all the states, you just won't know, right? And this is kind of natural because there could always be a lot of reward hiding under kind of one state, but unless you see it, you just don't know. Okay, so this is a kind of key idea, key challenge, I would say, in reinforcement learning is exploration. So you need to be able to explore the state space. This is different from normal machine learning where data just comes in passively and you learn a nice function and then you're done. Here you actually have to figure out how to get the data. And that's kind of one of the key challenges of RL. So we're going to go back to this problem. And I'm not really going to try to solve it now. For now, you can just think about pi as a random policy because a random policy eventually will just hit everything for finite small state spaces. Okay, so that's basically the end of the first algorithm. Let me just write this over here. So algorithms, we have model-based Monte Carlo. And the model-based is referring to the fact that we're estimating a model, in particular the MDP. The Monte Carlo part is just referring to the fact that we're using samples to estimate a model, or you're basically applying the policy multiple times and then estimating the model based on averages. Okay, so now I'm going to present a different algorithm, and it's called Modelfree Monte Carlo. And you might, from the name, guess what we might want to do is maybe we don't have to estimate this model. Okay, and why is that? Well, what did we do with this model? What we did was we, presumably use value iteration to, compute the optimal policy. And remember this recurrence for computing Q-opt. It's in terms of t and reward. But at the end of the day, all you need is Q-opt. If I told you Q-opt SA, which is what is Q-opt SA? It's the maximum possible utility I could get if I am in chance node SA and I follow the optimal policy. So clearly, if I knew that, then I would just produce the optimal policy and I would be done. I don't even need to understand the rewards and transitions. Okay, so with that insight is model-free learning, which is that we're just going to try to estimate Q-opt directly. Sometimes it can be a little bit confusing what is meant by model-free. So Q-opt itself, you can think about it as a model, but in the context of MDPs and reinforcement learning, generally people, when they say model-free, refers to the fact that there's no MDP model, not that there's no model in general. Okay, so we're not going to get to Q-opt yet. That'll come later in the lecture. So let's warm up a little bit. So here's our data staring at us. Remember, let's look at a related quantity. So QPi. Remember what QPi is. QPi of SA is the expected utility if we start at S and you first take action A and then follow policy pi, right? So in I guess another way to write this is if you are at a particular time step t, you can define ut as the discounted sum of the rewards from that point on, which is the reward immediately that you would get plus a discounted in the next time step plus a square discounted in the 2 time steps in the future and so on. And what you can do is you can try to estimate QPi from this utility, right? So this is the utility that you get at a particular time step. So suppose you do the following. So suppose you average the utilities that you get only on the time steps where I was in a particular state S and I took an action A. Okay, so you have let's suppose you have a bunch of episodes, right? So here pictorially, let's see. Here's another way to think about it. So I get a bunch of episodes. I'm going to do some abstract drawing here. So every time you have, SA shows up here, maybe it shows up here, maybe it shows up here, maybe it shows up here, you're going to look at how much reward did I get from that point on? How much reward did I get from here on? How much reward do I get from here on? And average them, right? So, and there's a kind of a technicality, which is that if SA appears here and it also appears after it, then I'm not going to count that because I'm kind of, if I do both, I'm kind of double counting. In fact, it works both ways, but just conceptually, it's easier to think about just taking the an SA if the same, you don't kind of go back to the same position. Okay, so let's do that on a concrete example. So Q pi, let's just write it. Q pi SA is a thing where we're trying to estimate. And this is a value associated with every chance node SA. So in particular, I've drawn it here. I need a value here and a value here. Okay. So suppose I get some data, I stay, and then I go to the end. So what's my utility here? It's not a trick question. 4, yes. Sum of 4 is 4. Okay, so now I can say, okay, it's 4. That's my best guess so far. I mean, I haven't seen anything else. Maybe it's 4. So what happens if I play the game again and I get 4, 4? So what's the utility here? 8. So then I update this to the average of 4 and 8. I do it again, I get 16. Then I average in the 16. Okay? And again, I'm using state, so I don't learn anything about this. In practice, you would actually go explore this and figure out how much utility is sitting there. So in particular, notice I'm not updating the rewards nor the transitions because I'm model free. I just care about the Q values that I get, which are the values that sit at the nodes, not on the edges. Okay, so one caveat is that we are estimating Q pi, not Q opt. We'll revisit this later. And another thing to kind of note is the difference between what is called on policy and off policy. Okay, so in reinforcement learning, you're always following some policy to get around the world, right? And that's generally called the exploration policy or the control policy. And then there's usually some other thing that you're trying to estimate, usually the value of a particular policy. And that policy could be the same or could be different. So on policy means that we're estimating the value of the policy that we're following, the data generating policy. Off policy means that we're not. Okay? So, so in particular, is model-free Monte Carlo on policy or off policy? It's on policy because I'm estimating Q pi, not Q opt. Okay, that's on policy. And off policy, what about model-based Monte Carlo? I mean, it's a little bit of a slightly weird question, but in model-based Monte Carlo, we're following some policy, maybe even random policy, but we're estimating the transitions and rewards. And from that, we can compute the optimal policy. So you can think about it as a off policy, but that's maybe not completely standard. Okay, so any questions about what model-free Monte Carlo is doing? So let me just actually write. So what is model-based Monte Carlo is doing? It's trying to estimate the transition and rewards, and model-free Monte Carlo is trying to estimate the Q pi. Okay, and just as a note, I put hats on any letter that is supposed to be a quantity that's estimated from data, and that's what I guess statisticians do. To differentiate them between when I write Q pi, that's the true value of that policy, which I don't have. Okay, any questions about model-free Monte Carlo? Both of these algorithms are pretty simple, right? You just, you look at the data and you take averages. Yeah?
So Modelfree is not trying to optimize your policy at all? You're not making changes to your policy?
So the question is model free making changes to a policy or is it fixed policy? So this version I've given you is only for a fixed policy. The general idea of model free, as we'll see later, you can also optimize a policy. Okay, so now what we're going to do is we're going to do theme and variations on model-free Monte Carlo. Actually, it's going to be the same algorithm, but I just want to interpret it in kind of slightly different ways that will help us generalize it in the future. Yeah?
Are there certain problems where model-free does better than model-based?
Are there certain problems where model-free is better than model-based? So this is actually a really interesting question, right? So you can show that if your model is correct, if your model of the world is correct, model-based is kind of the way to go because it will be more sample efficient, meaning that you need fewer data points. But it's really hard to get the model correct in the real world. So recently, especially with deep reinforcement learning, people have gotten a lot of mileage by just going model-free because then jumping ahead a little bit, you can model this as a kind of a deep neural network, and that gives you extraordinary flexibility and power without having to solve the hard problem of constructing the MDP. Okay, so there's kind of three ways you can think about this. So the first, we already talked about it, is this average idea. So we're just looking at the utilities that you see whenever you counter an S and an A, and you just average them. Okay, so here is an equivalent formulation. And the way it works is that for every SAU that you see, so every time you see a particular SAU, and so on, I'm going to perform the following update. So I'm going to take my existing value and I'm going to do what I call a convex combination. So 1 minus eta and eta sum to 1. So it's kind of balancing between two things, balancing between the old value that I had and the new utility that I saw. Okay, and the eta is set to be 1 over 1 plus the number of updates. Okay, so let me do a concrete example. I think it will make this very clear what's going on. So suppose my data looks like this. So I get 4 and then a 1 and a 1. So these are the utilities, right? That's a U here. I'm ignoring the S and the A. I'm just going to assume that there's something. Okay, so first, let's assume that Q pi is 0. Okay, so the first time I do, let's see, number of updates, I haven't done anything. So it's 1 minus 0, so 0 times 0 plus 1 times 4, which is the first U that comes in. Okay, so this is 4. Okay, so then what about the next data point that comes in? So I'm going to take 1/2 now times 4 plus 1/2 times 1, which is a new value that comes in. And that is, I'm going to write it as 4 plus 1 over 2. Okay, so now, okay, just to keep track of things, this results in this results in this. And then now, I'm running out of space, but hopefully I can. So now on the third one, I do 2/3. So I have 4 plus 1 over 2 times 2/3 plus, actually, I guess I should do 2/3 to be consistent. 2/3 times 4 plus 1 over 2, which is the previous value that's sitting in Q pi, plus a 1/3 times 1, which is a new value. And that gives me 4 plus 1 plus 1 over 3, right? So you can see what's going on here is that each time I have this sum over all the utilities I've seen over the number of times it occurs. And this eta is set so that next time I kind of cancel out the old count and I add the new count to the denominator. And it kind of all works out so that at every time step, what actually is in Q pi is just the plain average over all the numbers I've seen before. Okay, this is just kind of an algebraic trick to get this original formulation, which is a notion of average, into this formulation, which is a notion of kind of you're trying to take a little bit of the old thing and add a little bit of a new thing. Okay, so I guess I'm going to call this, combination, I guess. So that's the second interpretation. There's a third interpretation here, which you can think about it as in terms of stochastic gradient descent. So this is actually a kind of a simple algebraic manipulation. So if you look at this expression, what is this? So you have 1 times q pi. So I'm going to pull it out and put it down here. And then I'm going to have minus eta times q pi. That's this thing. And then I also have a eta a u. So I'm going to put kind of minus a u here. And this is inside this paren. So if you just do the algebra, you can see that these two are equivalent. So what's the point of this? Right, so where have you kind of seen this before? Something like, maybe not this exact expression, but something like it. Any ideas? Yeah, when you looked at stochastic gradient descent in the context of the square laws for linear regression, right? So remember, we had these updates that all looked like kind of prediction minus target, which was the residual, and that was used to kind of update. So one way to interpret this is this is kind of implicitly trying to do stochastic gradient descent on the objective, which is a squared loss on the q pi value that you're trying to set, and u, which is the new piece of data that you got. So think about in regression, this is the y. This is what the output is, and this is the model that's trying to predict it, and you want those to be close to each other. Okay. Okay. So those are kind of 3 views on basically this idea of averaging or incremental updates. Okay. So it'll become clear why I did this. This isn't just to have fun. Okay, so now let's see an example of model-free Monte Carlo in action on this the Volcano game. So remember here we have this mechanic example, and I'm going to set the number of episodes to, let's say, 1,000. Let's see what happens. So here, okay, so what is this kind of grid-like structure, grid of triangles denote? So this, remember, is a state. This is 2, 1. So what I'm doing here is dividing into 4 pieces which correspond to the 4 different actions. So this triangle is 2, 1 north. This triangle is 2, 1 east, and so on. Okay, so, and the number here is the q pi value that I'm estimating along the way. Okay, so the policy I'm using is complete random, just move randomly. And I run this 1,000 times, and we see that the average utility is minus 18, which is obviously not great. Okay, but this is an estimate of how well the random policy is doing. So as advertised, random policy you would expect to fall into a volcano quite often. Okay. And you can run this, and sometimes you get slightly different results, but it's pretty much stable around minus 19, minus 18. Okay, any questions about this before we move on to different algorithms? Okay, so model-based Monte Carlo, we're estimating the MDP. Model-free Monte Carlo, we're just estimating the Q values of a particular policy for now. Okay. So let's revisit what model-free Monte Carlo is doing. So if you use the policy pi equals state for the dice game, you might get a bunch of different trajectories that come out. These are possible episodes, And each episode you have a utility associated with it. And what Modelfree Monte Carlo is doing is it's using these utilities to kind of update towards update your QPy, right? So in particular, like for example, this you're saying, okay, I'm in the in state, and I take an action stay. What will happen? Well, in this case, I got 16, and this case I got 12. And notice that there's quite a bit of variance. So on average, this actually does the right thing, right? So just by definition, this is an unbiased estimate. If you do this a million times in average, you're just going to get the right value, which is 12 in this case. But the variance is huge. So if, for example, if you only do this a few times, you're not going to get 12. You might get something slightly related. So how can we kind of counteract this variance? So the key idea behind what we're going to call bootstrapping is that we actually have some more information here. So we have this QPy that we're estimating along the way, right? So this view is saying, okay, we're trying to estimate QPy, and then we're going to try to basically regress it against this data that we're seeing. But can we actually use QPy itself to help reduce the variance? So the idea here is I'm going to look at all the places where I start an in and I take stay. I get a 4. Okay, so I'm going to say I get a 4, but then after that point, I'm actually just going to substitute this 11 in. Okay, this is kind of weird, right? Because normally I would just see, okay, what would happen? But what happens is kind of random. On average, it's going to be right, but on any given case, I might get like 24 or something. And the hope here is that by using my current estimate, which isn't going to be right, because if it were right, I would be done. But hopefully, it's kind of somewhat right, and that will be better than using the kind of the raw rollout value. Yeah, question.
You would update your current estimate at the end of each episode.
Yeah, so the question is, would you update the current estimate after each episode? Yeah, so all of these algorithms, I haven't been explicit about it, is that you see an episode, you update after you see it, and then you get a new episode, and so on. Yeah. Sometimes you would even update before you're done with the episode. Okay, so let me show this this algorithm. So this is a new algorithm. It's called SARSA. Does anyone know why it's called SARSA? Oh yeah, right. So if you look at this, it spells SARSA, and that's literally the reason why it's called SARSA. So what does this algorithm say? So you're in a state S, you took action A, you got a reward, and then you ended up in state S prime, and then you took another action A prime. So for every kind of quintuple that you see, you're going to perform this update. Okay, so what is this update doing? So this is the convex combination, remember, that we saw from before, where you take a part of the old value, and then you try to merge it in with the new value. So what is the new value here? This is looking at just the immediate reward, not the full utility, just immediate reward, which is this 4 here. And you're adding the discount, which is 1 for now, of your estimate. And remember, what is the estimate trying to do? Estimate is trying to be the expectation of rewards that you will get in the future. So if this were actually QPy, not QPy hat, then this would actually just be strictly better, because that would be just reducing the variance. But of course, this is not exactly right. There's bias, so it's 11, not 12. But the hope is that this is not biased by too much. Okay, so these would be the kind of the values that you would be updating rather than these kind of raw values here. Okay, so just to kind of compare them, well, okay. Okay, any questions about what SARSA is doing before I move on? So maybe I'll write something to try to be helpful here. So Q pi, Modelfree Monte Carlo estimates Q pi based on U, and SARSA is still Q pi hat, but it's based on reward plus essentially Q pi hat. I mean, this is not like a valid expression, but hopefully it's some symbols that will evoke the right memories. Okay, so let's discuss the differences. So this whenever people say kind of bootstrapping in the context of reinforcement learning, this is kind of what they mean, is that instead of using U as the prediction target, you're using R plus Q pi. And this is kind of, you're pulling up yourself from your bootstraps because you're trying to estimate Q pi, but you don't know Q pi, but you're using Q pi to estimate it. Okay, so U is based on one path. In SARSA, you're based on the estimate, which is based on all your previous kind of experiences, which means that this is unbiased. Modelfree Monte Carlo is biased, but SARSA is biased. Monte Carlo has large variance. SARSA has smaller variance. And one, I guess, a consequence of the way the algorithm is set up is that Modelfree Monte Carlo, you have to kind of roll out the entire game. Basically, play the game or the MDP until you reach the terminal state, and then now you have your U to update. Whereas SARSA, or any sort of bootstrapping algorithm, you can just immediately update because all you need to do is you need to see this like a very local window of SARSA, and then you can just update. And that can happen kind of anywhere. You don't have to wait until the very end to get the value. Okay, so just as a quick sanity check, which of the following algorithms allows you to estimate Q-opt? Okay, so model-based Monte Carlo, model-free Monte Carlo, or SARSA? Okay, so I'll give you maybe 10 seconds to ponder this. Okay, how many of you need more time? Okay. Okay, let's get a report. I think I didn't reset it from last year, so this includes last year's participants. So model-based Monte Carlo allows you to get Q-opt, right? Because once you have the MVP, you can get whatever you want. You can get Q-opt. Model-free Monte Carlo estimates Q pi, doesn't estimate Q-opt. And SARSA also estimates Q pi, but doesn't estimate Q-opt. Okay. All right, so that's a kind of a problem. Like, I mean, these algorithms are fine for estimating the value of a policy, but you really want the optimal policy, right? In fact, these can be used to improve the policy as well because you can do something called policy improvement, which I didn't talk about. Once you have the Q values, you can define the new policy based on the Q values. But there's actually a kind of a more direct way to do this. Okay, so here's the kind of the mental framework you should have in your head. So there's two values, Q pi and Q-opt. So in MDPs, we saw that policy evaluation allows you to get Q pi, value iteration allows you to get Q-opt. And now we're doing reinforcement learning. And we saw model-free Monte Carlo and SARSA allow you to get Q pi. And now I'm going to show you a new algorithm called Q-learning that allows you to get Q-opt. So this gives you Q-opt, and it's based on reward plus Q-opt, kind of. Okay, so this is going to be very similar to SARSA. It's only going to differ by, essentially, as you might guess, the same difference between policy evaluation and value iteration. Okay, so it's helpful to go back to kind of the MDP recurrences. So even though MDP recurrences can only apply when you know the MDP, for deriving reinforcement learning algorithms, they can kind of give you inspiration for the actual algorithm. Okay, so remember a Q-opt. What is a Q-opt? The Q-opt is considering all possible successors, the probability, immediate reward plus future returns. Okay, so the Q-learning is this actually really kind of clever idea. And it could also be called SARS, I guess, but maybe you don't want to call it that. And what it does is as follows. So this has the same form, the convex combination of the old value and the new value, right? So what is the new value? So if you look at Q-opt is looking at different successors, reward plus V-opt. What we're going to do is, well, we're not going to be able to sum over all successors because we're in our reinforcement learning setting and we only saw one particular successor. So let's just use that successor. So on that successor, we're going to get the reward. So R is a stand-in for the actual reward, is the stand-in for the reward function. And then you have gamma times, and then V-opt, I'm going to replace it with our estimate of what V-opt is. And what should the estimate of V-opt be? So what relates V-opt to Q-opt? Yeah?
If you pick the A that maximizes Q-opt, that should be your V-opt.
Yeah, exactly. So if you define V-opt to be the max over all possible actions of Q-opt of S in that particular action, then this is V-opt, right? So Q is saying I'm at a chance node, what is the optimal utility I can get, provided I took an action. Clearly, the best thing to do if you're at a state is just choose the action that gives you the maximum of Q value that you get into. Okay, so that's just Q learning. So let's put it side by side with SARSA. Okay, so SARSA, these two are very similar, right? So SARSA, remember, updates against R plus Q pi. And now we're updating against R plus this max over Q opt. Okay? And you can see that SARSA requires knowing what action I'm going to take next, kind of a one-step look ahead, A prime, and it plugs it into here. Whereas Q-learning, it doesn't matter what A you took, because I'm just going to take the one that maximizes. Right? So you can see why SARSA is estimating the value of policy, because what A prime shows up here is a function of a policy. And here, I'm kind of insulated from that because I'm just taking the maximum overall actions. This is the same intuition as for value iteration versus policy evaluation. Okay, I'll pause here. Any questions? Q-learning versus SARSA. So is Q-learning on policy or off policy? It's off policy because I'm following whatever policy I'm following, and I get to estimate the value of the optimal policy, which is probably not the one I'm following, at least in the beginning. Okay, so let's look at the example here. So here's SARSA, and run it for 1,000 iterations. And like Modelfree Monte Carlo, I'm estimating that the average utility I'm getting is -20, and in particular, the values I'm getting are all very negative because this is Q pi. This is a policy I'm following, which is the random policy. If I replace this with Q, what happens? So first, notice that the average utility is still -19 because I actually haven't changed my exploration policy. I'm still doing random exploration. I'm still doing random exploration. But notice that the Q opt values are all around 20, right? And this is because the optimal policy, remember, is just this is a slip probability 0. So optimal policy is just to go down here and get your 20. Okay, and Q I guess it's kind of interesting that Q-learning, I'm just blindly following the policy, running off the cliff into the volcano all the time, but I'm learning something, and I'm learning how to behave optimally, even though I'm not behaving optimally. And that's the kind of a hallmark of off-policy learning. Okay, so any questions about these 4 algorithms? So model-based Monte Carlo, estimate the MDP, model-free Monte Carlo, estimate the Q value of this policy based on the actual returns that you get, the actual sum of the rewards. SARSA is bootstrapping, estimating the same thing, but with kind of a one-step look ahead. And Q-learning is like SARSA, except for I'm estimating the optimal instead of a fixed policy pi. Yeah?
Is SARSA on policy or off policy?
SARSA is on policy because I'm estimating Q pi. All right. Okay, so now let's talk about covering the unknown. So these are the algorithms. So at this point, if I just hand you some data, if I told you here's a fixed policy, here's some data, you can actually estimate all these quantities. But now there's a question of exploration, which we saw was really important because if you don't even see all the states, how can you possibly act optimally? So, so which exploration policy should you use? So here are kind of 2 extremes. So the first extreme is let's just set the exploration policy. So imagine we're doing Q-learning now. So you have this Q-opt estimate. So it's not the true Q-opt, but you have an estimate of Q-opt. The naive thing to do is just use that Q-opt, figure out which action is best, and just always do that action. Okay, so what happens when you do this is you don't do very well. So why don't you do very well? Because initially, well, you explore randomly, and soon you find the 2. And once you found the 2, you say, well, 2 is better than 0, 0, 0, so I'm just going to keep on going down to a 2, which is all exploitation, no exploration, right? So you don't realize that there's all this other stuff over here. So in the other direction, we have no exploitation, all exploration. Here, you kind of have the opposite setup where I'm running Q-learning, right? So as we saw before, I'm actually able to estimate the Q-opt values. So I learn a lot, but the average utility, which is the actual utility I'm getting by playing this game, is pretty bad. In particular, it's the utility you get from just moving randomly. So kind of what you really want to do is balance exploration, exploitation. So just kind of a side or a commentary is that I really feel reinforcement learning kind of captures life pretty well. Because in life, there's you don't know what's going on. You want to get rewards. You want to do well, but at the same time, you have to kind of learn about how the world works so that you can kind of improve your policy. So if you think about going to restaurants or finding the shortest path, better way to get to school or to work, or in research, even when you're trying to figure out a problem, you can work on the thing that you know how to do and will definitely work, or do you try to do something new in hopes of you learning something, but maybe it won't get you as high reward. So hopefully reinforcement learning is, I don't know, it's kind of a metaphor for life in many ways. Okay, so back to concrete stuff. So here is one way you can balance exploration and exploitation, right? So it's called the epsilon greedy policy. And this assumes that you're doing something like Q-learning, so you have these Q-up values. And the idea is that, with probability 1 minus epsilon, where epsilon is, let's say like 0.1, you're just going to give exploit. You're just going to give it all you have. And then once in a while, you're just going to do something random. Okay? So this is actually not a bad policy to act in life. So once in a while, maybe you should just do something random and kind of see what happens. So if you do this, what do you get? Okay, so what I've done here is I've set epsilon to be starting with 1. So 1 is all exploration. And then I'm going to change the value a third of the way into 0.5. And then I'm going to, 2/3 of the way, I'm going to change it to 0. Okay, so if I do this, then I actually estimate the values really, really well. And also I get utility, which is pretty good, 32. Okay. And this is also kind of something that happens as you get older. You tend to explore less and exploit more. It just happens. Okay. All right. So that was exploration. So let's put some stuff on the board here. Do I need this anymore? Maybe I don't need this. Okay. Okay, so covering the unknown. So we talked about exploration, epsilon greedy. And there's other ways to do this. Epsilon greedy is just kind of the simplest thing that actually works remarkably well. Even in state-of-the-art systems. So the other problem now I'm going to talk about is generalization. So remember when we said exploration, well, if you don't see a particular state, then you don't know what to do with this. I mean, if you think about it for a moment, that's kind of unreasonable because in life, you're never going to be in the exact same situation, and yet we need to be able to act properly, right? So the general problem is that the state space that you might deal with in a kind of a real world situation is enormous. And there's no way you're going to go track down every possible state. Okay, so this state space is actually not that enormous, but this is the biggest state space I could draw on the screen. And you can see that this, the average utility is pretty bad here. Okay, so what can we do about this? So I guess let's talk about large state space. So this is the problem. So now this is where the third interpretation of model-free Monte Carlo will come in handy. So let's take a look at Q-learning. Okay, so in the context of SGD, it looks like this, right? So it's a kind of a gradient step where you take the old value and you minus eta and something that kind of looks like it could be a gradient, which is the residual here. So one thing to note is that under the kind of formulations of Q-learning that I've talked about so far, this is what we call kind of rote learning, right? Which if we were 2 weeks ago, we would have said this is kind of ridiculous because it's not really learning or generalizing at all. Right now, it's basically for every single state in action, I have a value. If I have a different state in action, completely different value. There's no kind of sharing of information. And naturally, if I do that, I can't generalize between states and actions. Okay, so here's the key idea that will allow us to actually overcome this. So it's called function approximation in the context of reinforcement learning. In normal machine learning, it's just called normal machine learning. So the way it works is this. So we're going to define this QOpt SA. It's not going to be a lookup table. It's going to depend on some parameters here, W. And I'm going to define this function to be W dot phi SA. Okay, so I'm going to define this feature vector very similar to how we did in kind of in the machine learning section, like except for instead of SA we had X. And now the weights are going to be kind of this, same. Okay, so what kind of features might you have? You might have, for example, features on actions. So these are indicator features. that say, hey, maybe it's better to go east than to go west, or maybe it's better to be in the 5th row, or it's good to be in the 6th column, and things like that. So you have a smaller set of features, and you try to use that to kind of generalize across all the different states that you might see. So what this looks like is now with the features is actually the same as before, except for now we have something that really looks like the machine learning lectures, is that you take your weight vector and you do an update of the residual times the feature vector. Okay? So how many of you, this looks familiar from linear regression? Okay. All right, so just a contrast. So before we were just updating the Q-opt values, but the residual is exactly the same, and there's nothing over here. And now what we're doing is we're updating not the Q values, we're updating the weights. The residual is the same, and the thing that connects the Q values with the residual with the weights is the kind of the feature vector. Okay. As a sanity check, this has the same dimension. This is a vector. This is a scalar. This is a vector which has the same dimensionality as W. Okay? And if you want to derive this, you can actually think about the implied objective function as just simply linear regression. You have a model that's trying to predict a value from an input, SA. So SA is like X, and Q-opt is like kind of Y. And then this target is like the Y that you're trying to predict, and you're just trying to make this prediction close to the target. Yeah, question?
Is the eta the same as eta that we had before, or now can we set it like the learning rate?
Yeah, so a good question. So what is this eta now? Is it the same as before, or is it new? So when we first started talking about these algorithms, right, eta was supposed to be 1 over the number of updates and so on. But once you get it into the SGD form like this, then now this just behaves as a step size, and you can tune it to your heart's content. All right, so that's all I'll say about these two challenges. One is, how do you do exploration? You can use epsilon greedy, which allows you to kind of balance exploration with exploitation. And then the second thing is that for large state spaces, epsilon greedy isn't going to cut it, because you're not going to see all the states, even if you try really hard. And you need something like function approximation to tell you about new states that you fundamentally haven't seen before. Okay, so summary so far. Online learning, we're in the online setting. This is the game of reinforcement learning. You have to learn and take actions in real world. One of the key challenges is this exploration trade-off. We saw 4 algorithms. There's kind of 2 key ideas here. One is Monte Carlo, which is that from data alone, you can basically use averages to estimate quantities that you care about, for example, transitions, rewards, and Q values. And the second key idea is this bootstrapping, which shows up in SARSA and Q-learning, which is that you're updating towards a target that depends on your estimate of what you're trying to predict, not just the kind of raw data that you see. Okay, so now I'm going to maybe step back a little bit and talk about reinforcement learning in the context of some kind of other things. So there's kind of 2 things that happened when we went from binary classification, which was 2 weeks ago, to reinforcement learning now. And it's worth kind of decoupling these 2 things. One is state and one is feedback. So the idea about partial feedback is that you can only learn about actions you take, right? I mean, this is kind of obvious in reinforcement learning. If you don't quit in this game, you'll never know how much money you'll get. And the other idea is the notion of state, which is that rewards depend on previous actions. So if you're going through a volcano, you have to, there's a kind of a different situation depending on where you are in the map. And there's actually kind of, so this is kind of, you can draw a 2x2 grid where you go from supervised learning, which is stateless and full feedback, right? So there's no state. Every iteration, you just get a new example. And that doesn't have, there's no dependency in terms of prediction on the previous examples. And full feedback, because in supervised learning, you're told which is the correct label. Even if there might be 1,000 labels, for example, in image classification, you're just told which one's the correct label. And now in reinforcement learning, both of those are made harder. There's two other interesting points. So what is called multi-arm bandits is kind of you can think about it as a warm-up to reinforcement learning, where there's partial feedback, but there's no state, which makes it easier. And there's also, you can get full feedback, but there's state. So in structure prediction, for example, in machine translation, you're told what the translation output should be, but clearly the actions depend on previous actions because you can't just translate words in isolation, essentially. Okay, so one of the things I'll just mention very briefly is, this deep reinforcement learning has been, very popular in recent years. So reinforcement learning, there was kind of a lot of interest in the kind of 90s where a lot of the algorithms were kind of, in theory, was kind of developed. And then there was a period where kind of not as much happened. And since, I guess 2013, there's been a revival of reinforcement research. A lot of it's due to, I guess, at the DeepMind, where they published a paper showing how they can use raw reinforcement learning to play Atari. So this will be talked about more in the section this Friday. But the basic idea of deep reinforcement learning, just to kind of demystify things, is that you're using a neural network for QOpt. Essentially, that's what it is. And there's also a lot of tricks to make this kind of work, which are necessary when you're dealing with enormous state spaces. So one of the things that's different about deep reinforcement learning is that people are much more ambitious about handling problems where the state spaces are kind of enormous. So for this, the state is just the pixels, right? So there's a huge number of pixels. And whereas before people were kind of in what is known as a tabular case, which there's the number of states you can kind of enumerate. So there's a lot of kind of details here to get right. One general comment is that reinforcement learning is it's really hard, right? Because of the statefulness and also the delayed feedback. So just when you're maybe thinking about final projects, I mean, it's a really cool area, but don't underestimate how much work and compute you need to do. Some other things I won't have the time to talk about is, so far we've talked about methods that try to estimate the Q function. There's also a way to even do without the Q function and just try to estimate the policy directly. That's called methods like policy gradient. There's also methods like actor-critic that try to combine of these value-based methods and policy-based methods. These are used in DeepMind's AlphaGo and AlphaZero programs for crushing humans at Go. This actually will be deferred to next week's section because this is in the context of games. There's a bunch of other applications. You can fly helicopters, play backgammon. This is actually one of the early examples. TD Gammon was one of the early examples in the early 90s on kind of one of the success stories of using reinforcement learning, in particular, self-play. For non-games, reinforcement learning can be used to kind of do elevator scheduling and managing data centers and so on. Okay, so that concludes the section on Markov decision processes, the idea is that we are playing against nature. So nature is kind of random, but kind of neutral. Next time, we're going to play against an opponent where they're out to get us. So we'll see about that.